Seminar. So let me say a few words to introduce today's speaker, Dr. Johnny Luo from the City College of New York in the city, New York City. He did his bachelor's degree in atmospheric science at Peking University. Then he came to Columbia for his graduate studies, where he worked with Dr. William Rossau at GISS, at Goddard Institute for Space Studies. And his PhD thesis was on cirrus cloud, on convection associated with cirrus cloud. And after getting his PhD, he spent 3 years at Colorado State University, where he worked with Graham Stevens, and he did further work on clouds and deep convection. And then subsequently he joined the faculty at City College of New York, where he has been very, very active and productive. He, just to give a measure of his contribution, he is a science team member of NASA CloudSat program, also a science team member of NOAA Climate Data Record program. He's also a science team member of Mosaic, which is the measurement of ozone and water vapor of Airbus, sponsored by the European Union. And previously he was a science team member of NASA Energy and Water Cycle program. He has, in 2012 and 2011, he convened special AGU sessions in the fall meeting in San Francisco on tropical convection. So with all this activity and his contributions to the science and to the department, he was promoted ahead of schedule to the position of associate professor with tenure. So it's a great pleasure to welcome Dr. Johnny Luo.
Okay. Well, thank you for the introduction. It's a great honor to, let me turn on this first. Hello? 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 Yeah. Can you hear me? Okay, so I can use this.
You want to use this? I think you can use that.
Yeah, that's right. Okay, I'll just use this. It's a great honor to be here, and this is actually my first time, as I told Sultan a little bit earlier, although I'm only 2 hours away from Stony Brook, but I've never actually visited Stony Brook. It's a great honor. Thank you for inviting me. So today I'm going to just talk about a very simple concept in meteorology, level of neutral buoyancy. So if you're a meteorology major, most of you have learned this concept at the very early stage of your curriculum. So here I'm just gonna give a very brief kind of introduction of what level of neutral buoyancy is, just in case you are from a different field. So these are the slides I took from my my class, the class I gave. So you can visualize the level of neutral buoyancy this way. Imagine that the sun hits the surface, so the surface air gets heated, so become buoyant, warmer, buoyant, starts to rise. So as it rises, it will get colder, rise dry adiabatically, gets colder until the point that it gets saturated and then cloud forms. So that's a level we call lifting condensation level. So it's basically the cloud base. So if you go outside and see the cloud base is so clear cut, that's because that level is set by this process. Then clouds will continue to rise by some forcing, and it will pass the level free convection. It will continue to rise by itself. So it will grow and grow. Eventually, it will hit a point where the temperature of air parcel is equal to the temperature of the environment again. Okay, so that's the level we call the level of neutral buoyancy. And that's also, visually speaking, it's the level where you see these amber clouds developing, extending outside. So that's what we learned from textbook. It's the parcel theory definition of the level of neutral buoyancy. Okay, we adopting the pseudo-adiabatic version so that we don't get complication from the drag from the particles. So, well, eventually this convection may be vigorous and it may overshoot, just like those tops overshooting. But that's basically the level I'm going to talk about in this whole seminar. Okay, it's very simple. You learn this from day one when you are sign up for becoming a meteorologist. So the question I ask myself is that there is, if you think deeper, there are a few problems with this kind of definition of level of mutual buoyancy. First of all, we haven't talked anything about entrainment. So this whole air parcel go undiluted upwards. Okay. In reality, there might be some entrainment, exchange of mass, energy with the environment. Also, we only consider the thermodynamics in the whole picture, temperature, pressure, but we never consider dynamics. So when air wants to rise, it will meet resistance from the air surrounding it. So it's not that easy to go like this. There is no freezing effect. This hasn't been brought up until 2003, a paper by Ed Zipser. He pointed out that when when the water particle freezes, they will actually eject an extra level of energy, the fusion, latent heat of fusion, into the air parcel that can invigorate the air parcel, just give you a boost. So those effects are ignored. Finally, people can argue that the representativeness of the sounding, so what you call the sounding, the environmental temperature, is ambiguous. Okay, so it may not be what your balloon measures over the 50-kilometer scale. It might be some temperature immediate next to the air parcel. So those questions are actually something we should consider. Okay, so the study, the questions I asked myself when I did this study is, how relevant is this kind of definition of level of mutual buoyancy, like the parcel theory, undiluted version, to the predicting the actual deep convective outflow? So suppose you're handed over a sounding. I want you to tell me the level of mutual buoyancy. You can give me a number, but how useful, how realistic, how relevant is that number to the real actual convective outflow? Okay. The second question I think is that it's related, because we can use, we have a sounding version of LNB, but at the same time, the level of mutual buoyancy can be estimated by just observing the actual development of convective clouds. You just take a look at the convective clouds, you can tell envelope develops here, that's the level of mutual buoyancy. So that's something we call the level of mutual buoyancy underscore observation. So there are two versions of the level of mutual buoyancy. One is theoretical definition, the other is from observation. So I want to ask how are they related? So when we compare the level of mutual buoyancy from sounding, from level of mutual buoyancy from observation, so we might see some differences. Then the deeper question I ask myself is, what do the differences tell you about the underlying convective dynamics, the processes? So those things are kind of the underpinning questions of my study. Okay, so now I'll give you an outline. That's the presentation 101. You have to give the audience the outline, otherwise they get lost. So what I'm going to follow first, I'm going to introduce the methodology of my observation, how I analyze the data to derive the LNB. Also, after that, I'm going to show you some global statistics on level of mutual buoyancy, and then move on to the detail, the regional differences of the LNB. Then I'm going to show a few related studies. Some of the studies figures are fresh out from my students maybe early this week, so I can't explain everything, but I'm gonna show some of them. Okay, let's go to the first one. Let's take a look at the LNB sounding. This is a level of mutual buoyancy from sounding calculated from ECMWF analysis. So whenever satellite observes a deep convection, okay, in the tropics, we analyze the data from 2006 to 2008. So you can see some features here. I'm gonna walk you through a little bit. So the tropical mean is about 13.6 kilometer. And what first stands out in this figure is actually in the West Pacific, tropical West Pacific and Southeast Asian monsoon region, you can see the level of mutual buoyancy is a lot higher. So I would say those regions are friendlier to deep convective developments. Okay, so also what you see is that African, where we know that there are some very strong, intense convection, deep convection, but in terms of level of mutual buoyancy from sounding, they actually fall behind. Okay? And if you go to the East Pacific, where it's the ITCZ band, very narrow band, you see that the value is rather small. It's something like 12 kilometers. So it falls further behind Africa. So those are some of the features we see.
Yeah, I have a question.
Yeah, go ahead.
So you did this analysis using DSMW analysis, but how good are the analysis in terms of determining that?
Perfect. That's the question the reviewer asked when I published the paper. I mean, over ocean, it's hard to give a one-sentence answer, but I would say it's reasonably well. We cited some papers, but another point I want to make is that this is probably the only source we have to match the satellite. If we limit ourselves to sounding and then match satellite observation of convection, then probably over the whole 4 years we'll only have maybe 12 data sets points to play with. So that's the first step. But that's a valid question. We should go into that 12 cases and validate and see how good the quality is.
Which procedure you use for level 1 performance?
Which one?
What's the difference? How you define your parcel and the boundary layer? This, that.
Yeah, we use those details. We use the lowest 500 meters, the highest moist static energy, as the launching point.
So it's
So
like
launch-
you use the pseudo-adiabatically, right?
We use what?
Pseudo-adiabatically, like with
We use pseudo-adiabatic. Yes,
with
pseudo-adiabatic.
precipitation forming.
Right. That's the version we use. Yeah. If you introduce the, yes. Also, we ignored the ice processes so that there is no boost from the fusion latent heat. So if you do that, it will add another 500 meters to
So
you.
this is an annual mean, is that correct?
Longer than that. Yes. From
So
2006.
is this calculated from the annual mean conditions, or is this the annual mean of, say, daily or monthly?
Any mean of instantaneous
Of instantaneous?
events. Yeah.
Okay.
Instantaneous events. It's a good question. Yeah. Okay, so the object of this study is that's the version we call level of neutral buoyancy from sounding. One version of it, pseudo-adiabatic, using ECMWF analysis, operational analysis. So the object of this study is to analyze the observed deep convective clouds to determine this level of neutral buoyancy and compare them with this version of sounding. So now it's straightforward, because that's our target of analysis. So you just look at the clouds, look at the picture, you can easily tell that the well-defined, well-developed amble like this, and outflow, they can tell you something about where the convective motion lose steam and start outflow. Just conceptually, it's straightforward. But observationally, how you define it? So I'm going to introduce the data set I used. So the data set I used is observation uses from CloudSat. So CloudSat, how many of you have heard of this satellite CloudSat? Not too many, so I better spend a little bit of time on it. So CloudSat is one of the NASA mission that puts a cloud providing radar into space. So it's part of the A train. It's a train of satellites flying one after another. So very close, they make measurements almost simultaneously. So CloudSat is a radar, that's Calypso is a LiDAR. Aqua has a bunch of instruments like MODIS, M3E, Cirrus, and Aura is another one that's on the back. Parasol is a French satellite studying aerosol. So those satellites form a train. So, but I'm going to focus on CloudSat for this talk. So CloudSat is a 94 gigahertz, about 3 millimeter radar. So it's not the weather precipitation radar you see daily on weather channel. That's a centimeter radar. It's sensitive to rain. But this one is sensitive to both cloud particles and raindrops. But just keep in mind that severe rain can attenuate the signal. The sensitivity is very high. It's minus 30 dBz. And the footprint is relatively fine, only 2 by 1 kilometer roughly footprint. And vertical resolution, since the radar can profile things, so give you a vertical profile of the clouds at 240 meter scale. And because they follow a sun-synchronous orbit, so the equator crossing time is 1:30 a.m. and p.m. Just keep that in mind. Everything I showed you today is going to be convection of 1:30 a.m. and p.m. Okay, so that's kind of the drawback. I mean the downside. But for now, that's the best we can do. Just give you some kind of a visualization of what CloudSat sees. So I use the geostationary satellite. I pick out some kind of a tropical African, that's Africa, some convection here. So zoom in, then I showed what A train sees these hot towers convection. The top one shows this segment oriented opposite, 90 degree. That's the longitude, that's the latitude. So show you the 11 micron brightness temperature. Basically, that's the cloud top temperature. You can see the value is very low. Some of the towers are lower than 200 Kelvin, very cold. Okay. This line is where CloudSat, the footprint of CloudSat. Now, this second figure shows you the answer E. It's a microwave radiometer. The answer E, 89 gigahertz brightness temperature. So what this instrument can tell you are basically the objects of convection. So it takes a whole class to explain what this value means, but basically microwave radiation at very high frequency, they are scattered by large ice particles, so that if there's a large ice particle objects, then these brightness temperature are extremely low, lower than sometimes 150 Kelvin. So these centers are the convective core inside this code, buried in the code deck. Now CloudSat cuts through here, so you can see the vertical cross-section surface, 20 kilometer along this latitude. So you can see this convective core. That's radar reflectivity. So you can see the structure of the convective core here. Yeah, so that's kind of CloudSat view. It also shows the ample clouds, which non-core, these clouds. How many of you have heard of the satellite called TRIM, Tropical Rainfall Measuring Mission? So more than CloudSat. That's good, because I'm going to show you a simultaneous view from TRIM. So if you're more familiarized with the satellite called TRIM, okay, TRIM is a centimeter radar. The reason I show this image is because it's a lucky day for us, because that day, TRIM happens to pass by the same place at the same time. So we get a simultaneous view from the TRIM. Okay? So you can see these convective towers are easily picked up by TRIM, but the rest of the envelope of the clouds are missed from TRIM. So that's the difference between between centimeter radar and millimeter radar. Centimeter radar is what you see from weather channel that picks up the rain, but cloud radar is what picks up both clouds and rain. So that's kind of the difference. Okay, it's kind of observation. Now let's look into our methodology. So basically, we search our CloudSat database and search for the convective objects that looks like this. So we ask ourselves just where does the convection outflow, where does the convective motion lose spin and outflow. So the focus is, of course, the envelope that's attached directly to the convection, to the convective core. So we define level of neutral buoyancy in multiple ways. First, we use the top of the envelope. We call it level of neutral buoyancy _ cloud top height. So it's basically the level of neutral buoyancy, that's the tallest level. At the same time, we search where the maximum radar reflectivity is within the envelope and designating that level as the level of neutral buoyancy, what we call the maximum mass. Because as I'll show later, that this radar reflectivity basically tells you how much mass outflow is. So that's kind of your maximum mass outflow level. So for chemical transport people, that's a very important level because that's the majority of the mass that's been ejected into the upper troposphere. Similarly, we can define the level of neutral buoyancy based on the base height of this envelope. Okay, so just multiple ways of defining. Just keep in mind this figure because this is I'm going to show statistics from now on of these three numbers. There's a fourth number, of course, that's the theoretical calculation of level of neutral buoyancy from something. It's not really something, it's from ECMWF analysis. But
is your max mass level weighted by the entire anvil or just the
entire
outflow?
Entire.
Entire.
Yeah, I could down just for the, actually, that's the next point. I only analyzed the first 20 kilometers of the envelope. The reason for doing this is to minimize the ice sedimentation effect, because if you go too far, then the ice starts to sediment. It does not represent where the fresh ejection is. So So those are the methodology. Maybe I want to show more about this case I picked. It's a case in Amazon, Brazil. In here, that's the cloud-fed path, vertical cross-section of the cloud. That's the top-down view from MODIS. You see the code cloud top. And the lower one basically shows the combined view of radar and LiDAR. So this color is what's been picked up by LiDAR. The red color is what can be seen by both radar and LiDAR. And the greenish color is what's been seen by only radar. Okay? So you can see the synergy between LiDAR and radar. Radar can pick up the very thin tropical cirrus. It can pick up the top part of the convection, but it misses the lower part because of the heavy attenuation. But for radar cannot see the tropical cirrus, but it sees the bulk part of the convection. So just keep in mind that this is kind of a blind man filming the elephants. So one instrument alone, you cannot tell the whole elephant. But fortunately, we're only care about this part of the elephant, so it's okay for radar for now. Just want to show you some examples. That's the example I show you. But we have we searched all the data sets. We found 4,008 such cases from 2006 to 2008. And last week, this study has been expanded to all the years, so until now. So now we have about 8,000 cases. But when the paper was published, it was based on only 3 years of analysis.
Are those 8 the only ones that you had in that period, 6 to 8? 2006 to 2008?
Yeah. So all the statistics I'm going to show is from 2006 to 2008.
So you first identify a convective core with the size, say, limitation, then identify the angle associated.
Yeah. So exactly. We first search for the convective core with a certain criterion, like this guy, like this. Then we search left and right for the existence of angle, attached angle. If the case becomes too complicated, then we just throw them away. We just look for this so-called perfect case, because CloudSat it does a curtain sampling. Oftentimes it will miss the core or it will miss the angle. So whenever that happens, we call this an imperfect sample because it cannot tell us the information we want. So that's our selection.
It's an interesting variety, but unfortunately you don't know where in the whole anvil growth process you're taking your view. So these could be a lot more similar, but merely taken at different times.
Quite possibly. Yeah. So that's the caveat we bear.
Yeah.
Okay. So this figure shows the observation. Those are number of observations from each of these 10 by 10 grid box. So of these 4,000 cases, most of them are selected from tropical West Pacific, some from Amazon, some from Atlantic Ocean, but basically those are familiar, the usual suspect regions of where you can see tropical convection. So just give you a feel of where we found them. Okay, so much for the methodology. Let's go into the global statistics. If you just want to have a simple take-home message, I think this figure might serve the purpose because it shows you a number of quantities, tropical average for 3 years. So we show, that's the box representation, 25 percentile, 75 percentile, mean, median. So we show the sounding, level of future buoyancy based on sounding. We have 2 versions, but at this point you don't have to pay attention to the difference. You can read the paper for the difference, but they're almost identical. Okay, so what you can see here is that that's the level of future buoyancy for sounding. The mean medium is roughly 14 kilometers, slightly lower than 14 kilometers. Then this value shows the level of future buoyancy based on the cloud top height, based on this level. Okay, so I think the first message we see is that the level of future buoyancy from sounding is a reasonable upper bound for level of future buoyancy based on the identification of the height, the top of the envelope, because they're within about 500 meters. So that's considered, I would say, small enough. So, but still, it's just slightly above it. But it's interesting. We have 4,000 cases. When you do a 1-to-1 correlation, you might expect if this sounding LMB has a controlling power over observed outflow level, then you should expect some kind of correlation, one-to-one correlation. Higher sounding LMB, higher outflow. But it turns out that the linear correlation is only 0.29. It's very low. So that makes us think that although the sounding gives you the upper bound of the convection, it's not really tell you that much about exactly where the outflow will occur. Okay, so that's the first message.
And your
That
soundings
includes-
are all from ECMWF.
ECMWF, yeah, quote unquote sounding.
Yeah, right.
And this includes observations over both water and land?
Yes, I'm gonna show the separation. Yeah. I'm gonna show the separation. It's also in the paper. So the second message, which is also important, is that this level, which I used a bigger arrow, which I call the maximum mass outflow level based on radar reflectivity, happens to be actually on average, global average, tropical average, 3 kilometers lower than the sounding. Okay, it's quite low. What this tells you is that if you care about mass transport, the maximum of the mass gets ejected at a level that's much lower than what the sounding tells you where it should outflow. Okay, and also at the same time, the linear correlation is again very small. We also looked at the deep convective core, DCC. This part is the core. And also we looked at the highest point of the core. Okay, so we record these statistics for each convective object. So out of these 4,000 cases, we found that they actually goes very high. These are above the core is above the level of mutual buoyancy calculated from sounding because of the overshooting. And they actually shoot well into the tropopause layer because just consider 14 kilometers is the base of the TTL, then they shoot well into it, especially the highest point. So those should arouse some interest in the stratosphere-troposphere exchange community. Okay, that's the simple statistics. Now follow up your question, land versus ocean. Let's take a quick look at the statistics, land versus ocean. Let me draw your attention to this box first. That's the land versus ocean for the sounding. You don't have to pay attention to the difference between version 1, version 2. Let's look at the version 2, okay? And then that's the land-ocean difference in the quantity of cloud top height, maximum mass, cloud base height, version of the level of mutual buoyancy, ocean, land, okay? Also look at the deep convective core height, land, ocean. So just stare at these numbers just for a few seconds. I think the conclusion might be like this. That's how we interpret them. First, the level of mutual buoyancy based on sounding is pretty similar between land and ocean. So if you compare this number, they are different by, in my eye, is 50 meter or 40 meter. So those are very, very tiny, 40 meters, so very small. So we can say that's similar between land and ocean. However, if you compare the level of mutual buoyancy based on observation, all 3 versions, you can see that the land is consistently higher than the ocean counterparts by at least roughly 500 meters. Okay, so that's we run the statistics analysis. That's significant by any standard. So also you can see the core. Okay, the height of the core over land is also higher than the core of the ocean by roughly similar amount, 500 meters. So that's the first message you can take home. Ocean and land, the environment in terms of the level of mutual buoyancy is about similar, but the reality are different. So the land convection develops taller. We also looked at the size of the system. So our definition of this, we have 2 sizes. One is the size of the whole system, including the envelope, end to end. The other is the size of the deep convective core. Okay. So the first number is the median, the second number is the standard deviation. So you can see that the oceanic convection is bigger overall, 167 kilometer, versus the land convection, 140. But if you look at the core size, the core of the land convection is 14 kilometer, whereas the land convection is about 10 kilometers. So that basically says that oceanic convective systems are bigger. That's not a surprise. We see gigantic convection over ocean. Over many years of satellite observation, But if you look into the cold cloud depth inside, pick out those cores, what you will find is that the cores actually are smaller over ocean than over land. Okay? That's the second message. The third message, actually, we can calculate the entrainment rates based on this observation. So I'm going to elaborate a little bit on this because that might be helpful to the GCM cumulus parameterization. The way we calculate entrainment rates, let me first introduce the model of the entraining plume model. That's the model used in the many GCM parameterization to represent a convection. So basically, you have a conserved quantity, just generic, make it phi, say equivalent potential temperature. Environment value is phi prime. Inside the cloud is phi. So air mass dn mixed into the clouds, n of the particle inside the clouds. So you assume they're well mixed once they get entrained. So you get mass become m plus dn, the quantity become phi plus d phi. Okay, so you can do a conservation before mixing, after mixing. So you can expand this. Then cross out the common term, drop out the second order term. So what you have is three terms. And rearrange them, you get this. And then do the time derivative, you got that. Okay. So then you can further assume that the whole thing is in steady state. So you can replace anything dgt by w ddz. Okay. So if you do this, replace it, you get equation that looks like this. What this equation says is basically the change of this property phi over height inside the cloud is proportional to two things. One is the difference between the property outside the cloud and the property inside the cloud. The other is a fractional increase of the mass over height. And this parameter is a key parameter in cumulus parameterization in GCM, so it's called entrainment rate. Okay, so I'm going to use this simple model to estimate the entrainment rate. What we do is basically we use the moist static energy equivalent potential temperature. That's the saturated equivalent moist static energy. So you launch an air parcel from the surface, you give it various value of entrainment rates, so they will take different thermodynamic path. And then you iterate lambda entrainment rates until that the calculated MSE matches the observed, which is neutral buoyancy. You have to land on this spot on the saturated MSE. That makes it neutral buoyant outflow level. So that's kind of the methodology for every observed convective objects. If you have the environment profile, you can calculate the entrainment rates that's associated with this. Okay. So I'm just gonna show very briefly, you can go read the paper. The results we found, the average entrainment rates for all these, it's not, for every convective clouds, we calculate entrainment rates, then we average them. So for cloud top height level neutral buoyancy, the entrainment rate is roughly 3% per kN. For maximum mass, the entrainment rate is 6% per kN. Then for the cloud base height, it's about 10% per kN. So those are the values we can calculate. And this value, I believe, can be directly used to evaluate GCM cumulus parameterization. And a very interesting result we found is that entrainment rates are slightly larger over ocean, over land. So taking on the face value, what this tells you is that the oceanic convection is more diluted than continental. That's kind of not too much a surprise. When I showed this to Ed Zipster, he said, well, that's what we have known for 20, 30 years. We know that continental convection is vigorous, it's free of destruction from environment. So, but somehow this can validate his claim globally from satellite.
May I ask another question?
Yeah.
I missed the very beginning when you were talking, maybe this was answered, but is this data irrespective of latitude? So all you're separating land and ocean, what about latitude?
Actually, that's going to be in this part, regional differences.
Right.
You didn't miss anything.
Yep.
So, okay, so let's look at the regional difference. Everything I showed so far are in single numbers, either land versus ocean, but you can look into the maps. Okay, so that you can, let's spend some time on this. So level of neutral buoyancy from sounding that I showed I showed before. Level of mutual buoyancy based on the cloud top height, it's this figure. Level of mutual buoyancy based on the maximum outflow is this figure, and based on cloud base height is that figure. Okay, so maybe you can form your own judgment or conclusion from here, but the way we interpret this is that tropical West Pacific has the highest level of mutual buoyancy from sounding. That's obvious from here. But when you come to the observed version of the same story, what you found is that, let's take this one as an example, that tropical Africa starts to stand out. And Amazon as well, so you see the color become more and more reddish. In other words, that their level of mutual buoyancy based on the morphology of the clouds profile, they become taller. Okay, so the highest level of mutual buoyancy based on observation is actually over land, as well as the maritime continents. So that's something very interesting. Although partial theory says the tropical West Ocean should dominate, but what observation says, well, land plays a role. That's the first message. Also, we can look at the difference between level of mutual buoyancy based on sounding and level of mutual buoyancy based on observation. So what you can see here is a striking difference between land and ocean. So basically what it says is that the difference between these two levels, the dashed line and any of these solid lines, are much smaller over land than over ocean. So in other words, the land outflow can realize its potential closer to its full potential. So it pushes out closer to the partial theory determined the level of mutual buoyancy from partial theory. Okay, so you can see these numbers are a lot smaller than equivalent over ocean. So there's an alternative way of actually explaining this in terms of entrainment rates. So the land convection gets entrained less, it gets diluted less, so it can go up higher. The oceanic convection gets diluted more, so that it has to lose steam earlier because it gets diluted. That's kind of consistent with our estimates of entrainment rates, land versus ocean. We also estimated convective core height. So this part, that's what we call the core. And the core height minus level of mutual buoyancy based on cloud top height. Okay, so we also see that in general, the convective core is higher over land, especially Africa, Amazon, than over oceanic area. And the second figure is something very interesting. This quantity says that the core height minus the level of mutual buoyancy based on cloud top height. So what this says basically is what we call the overshooting distance. It overshoots the emerald deck. Okay, how much it overshoots. You can see that continental convection, this quantity is much larger than oceanic convection. So that it basically says that it should have more vigor continental convection. Okay, so which Zipser was very happy to see. Okay, so there's one last quantity I want to show. It's the highest point of deep convective tower. So basically, it's the highest point of the core. This point, okay, they show similar message. Land is larger over ocean, and the overshooting distance is greater over land than ocean in general, except Asian monsoon region. Well, this is considered land, maritime continent. So that's the general message. Okay, so let me move on to show a few related studies. Actually, there was a study based on field campaign observation by Malendor. Actually, they used one of the field campaign from Brazil. It's the train LBA field campaign. They captured one convective system using multiple radar. So they analyzed a similar problem. So it's called radar reflectivity as a proxy of convective transport, published in 2009. So remember, it's a single case. So what they found is interesting. That's the radar reflectivity of this convective system. And this is the vertical velocity based on Doppler velocity. And then when you do the vertical derivative of the vertical velocity, you get the divergence into the envelope, because the divergence has to be, vertical gradient of this vertical velocity needs to be balanced by divergence and convergence horizontally. So they can derive a profile of the divergence into the envelope. Okay, so what they found is that this divergence, this figure is the divergence. So the peak of the divergence into the envelope corresponds very well with the cloud, with the radar reflectivity. This one shows the liquid water content in the envelope. This one is also the liquid water content. So they have another figure actually shows the radar reflectivity. So this figure kind of give you the idea that you can use information in the radar reflectivity to tell you how much, to tell you the dynamics. The convergence is absolutely a dynamics parameter, but you can use the radar profile to tell you information about it. Recently, Monitor, they published another paper, 2013. They analyzed now 9 cases, because when it comes to field campaign analysis, your data, you cannot get thousands of data sets. She pulled out all her data set. She can get 9 points. So one consistent message she found is that this is the level of mutual buoyancy based on sounding. This is real sounding now. Okay, not the fake one I use. It's not fake one. It's unfair to say that one. This is the called level of maximum detriment, which corresponds to the maximum radar reflectivity level. So they found that consistently the level of mutual buoyancy by sounding are higher than the maximum mass outflow by roughly similar amount as I found in the paper, except this guy. So, but just keep in mind, this is kind of the sanity check using real field campaign. But I would argue that with this global data set we developed using CloudSat, we can answer questions not easily answered from field campaign. For example, we can ask, how do this observation, the level of mutual buoyancy outflow, depend on the convective system size? How does it depend on environmental conditions? So to answer those questions, you need large amount of statistics, thousands, tens of thousands of cases to investigate. So one of my graduate students' thesis is on this, and she found some results. These are fresh out, so I'm not sure I understand them fully. But let's walk through them. So the top one shows the composite level of mutual buoyancy based on sounding, sorted by relative humidity of mid-troposphere. This is actually motivated by a paper published by Mike and Tony Del Genio. They found that the middle troposphere humidity plays an important role in kind of a choking convection. So if it's really dry, it can easily choke a convection and never develop into deep convection or become cumulus congested. So that's the 500 millibar relative humidity sorting. This axis is the size of the convective system. Okay, so the arrow here I drew represents the gradient of LME with respect to the size and relative humidity. So what we found is that the sounding, the level of mutual buoyancy sounding will increase with the relative humidity in the middle troposphere, but it will decrease with size. So in other words, the sounding, the sounding environment somehow goes with the smaller convection and humid environment. Okay. So that's the first message. The second one is when you do the cloud top level of mutual buoyancy, it goes the other way. It prefers the bigger system, but also it likes the larger middle troposphere humidity. And then for the maximum mass outflow, it goes this way. It likes or basically it's similar to that. It likes humid middle troposphere, and it likes smaller system. And the base, that's the, and you can separate this land versus ocean. This is the version from ocean, and this is the version from land. I probably don't want to spend too much time on it. If you want to talk to me, we can talk offline because I'm running out of time. And also, these are fresh out. I'm not too sure how to explain these features. Okay. Maybe okay, don't want to attempt to do it. Let's do this offline. Okay, so let's look at what's the message from this talk, this analysis. We analyzed 5 years of CloudSat observations of convective objects, and they showed the following things. First, the level of mutual buoyancy based on sounding analysis is a reasonable upper bound for deconvection, convective outflow. However, when you do one-to-one correlation, you found correlation between observed level of outflow and sounding level of mutual buoyancy is very small. In other words, you cannot trust the sounding to tell you how high this convection will develop. Some other parameters.
This correlation is between pairs of co-located satellite data and then the sounding cake.
That's right. That's right. Yeah, exactly. So, yeah. So I think what it says is that you cannot rely only on the environmental parameters to tell you where the convection will outflow. Other things like entrainment will also play a role. Someday maybe there's a dynamics, there's wind shear that makes this convection entrain more than other days. Then that cloud is diluted more. So the second thing is the level of mutual buoyancy based on the maximum mass flux is more than 3 kilometers lower than sounding. And I think this has important implications for convective mass transport, because when I presented this to those UTLS chemistry people, they are very interested. They want to compare this to, they want to use this kind of as a guidance at which level their aircraft is going to fly. So these all 3 forms of level of mutual buoyancy based on observation are found to be higher over land than over ocean. So land deep convection more rigorous. Also, we found that the entrainment rates calculated from this observation are larger over ocean than over land. So ocean deep convection more diluted. Finally, I'm finished. This is actually last part of the student's thesis, is that we saw some dependence of this value upon the system size and the environment, but we're still trying to interpret what message it contains. But it's a great potential that they can tell us something very useful. There's one paper we recently published on GRL, and we're writing a second paper, a longer one. If you're interested, you can also go into my website. That contains some links and background of the group and study. Thank you very much.
Any questions with the guest, Bara?
Yeah, Johnny, you probably was familiar with Hartmann's fixed annual temperature hypothesis, and I'm pretty sure that you looked at that, right? How well it works, because you have all the tools here.
Okay, the question is this. So he asked about the Dennis Hartmann's fixed envelope temperature hypothesis. Basically, that hypothesis says that in the global warming scenario, convection will grow taller, but the emission temperature at the cloud top will remain fixed. So that's the idea.
Not only will, but it's actually fixed now too.
Okay.
So have you looked at that?
A short answer is I haven't, but Sue Vandenhever, we are working on this together. Her student is looking at this. Also, she's looking at iris hypothesis and things, how this envelope size depend on SST and things like was asked earlier.
That's the first thing I would look.
Yeah, of course, of course.
Just out of curiosity, did you look at what the correlation at a station? Have you looked at the correlation with the level of neutral buoyancy from station soundings and what the ECMWF would give you at that location? It's just a representativeness question.
Yeah. Short answer is no, I don't have the results to back this up. But we have publications in the past to evaluate the ECMW analysis sampling, the quality of them. So, but coming to these 4,000 cases I picked, that's what you care about most, right? So we haven't done this.
Yeah, I'm just curious if the correlation would be 0.7 or 0.5 or 0.9.
Oh, that. No, that's a good question. That's a good thing to investigate. Yeah, that's a good point.
What about ARM data? Is there good continental ARM data that, or?
Might be help answer.
think we could definitely do the same type of analysis with our data.
Yeah, absolutely. It should be straightforward. That means the methodology, if you think about it, it's just to identify
That's an
objects like
interesting
this.
cloud you had there.
Yeah, it's
Well,
well,
yeah,
yeah,
the previous.
it's a heavy downpouring day if you are sitting there. Yeah, but absolutely. R might get saturated at very heavy precipitation, but for the most part, the envelope should be reviewed by the skin.
It might also give you a better time development because they can sit there and.
Yeah,
you
that's a
know,
good idea.
yeah.
Actually, that's been done by another collaborator. It's been done by another collaborator at University of Michigan. His student is working on. I have another study which looks at the buoyancy. I use the A-train observation to estimate the instantaneous buoyancy of this tower. I have a method. So when we estimate this guy is positively buoyant, that means next point it's going to rise. So we use R to evaluate if that guy really rises. So most of the cases they do, but most of them are cumulus congestus. Like for this deep convective clouds, most of the top has negative buoyancy, so they will be pulled back. That's also what ARM shows.
Yes, Martin, another question here.
But have you segmented it by season or month at all?
I haven't at this point. We have 8,000 points. We can definitely subset them by season. Yeah, by month we might not have enough data.
Because
By
these
season.
things, we've looked at another thing I talked to you about, but these tend to wander about 20 degrees. The maximum convection, I think, goes about 20 degrees into the summer continent season. I was just curious.
Yeah, those are the
Yeah, whereas
annual average, but they may swing back and forth.
Yeah.
Okay, we'll look at that.
Vic, do you have a question?
Yes, up to actually. For the 2008 cases, were they all during the 1:30 p.m. and 1:30 a.m.?
Yes.
Okay, for that two specific time, does the ECMWF also provide you exactly the same time, or how close to those?
ECMWF is 6 hours, so it's interpolated spatially and temporally to that point.
That be my very largest concern.
Yeah.
ECMWF provides you 6 hours data. Each of your clouds actually does not last that long.
No. Yeah.
So it's approximation actually.
This actually goes back to the original question I raised. See, if the original motivation of this study, one of the questions is the representative of the sounding. So even if you have the sounding exactly at the same time, you might argue that what the convection experienced is not what the balloon measures. Because the immediate environment, the convective tower, might be warmer or colder, depending on the dynamics of what the balloon measures. So that's always a lingering question. It's a very good point.
Also the resolution of the ECMWF. You're actually consider the 1 box or what 2.5 by 2.5.
It's it's 1 by 1.
1 by 1. Okay, you're actually consider that 1 by 1 as an air parcel.
Right.
Right. That's two different.
So the idea there is that that is the best global data set.
Well, yes, we have lots of other sounding data can repeat the study just out of my curiosity. So that's
Yeah.
why I started.
It's a good point. Well taken. Point well taken.
Yeah, just a comment. So the entrainment rates are larger over the ocean than over the land.
Mm-hmm.
And the size of the convective course over the ocean is smaller than over the land.
Ocean's bigger. Yeah. Smaller.
So this is consistent with the classical lab
Yeah.
experiment that the entrainment rate is
Right.
inversely proportional to the size
That's right.
of the plume.
Sure.
Therefore, in your calculation, you have both the entrainment rate and you have the size for each system. Did you do a correlation?
That's a very good point. I'll do that.
Yeah,
I haven't.
because
It's a very good point.
Yeah, right now the formula is 0.42
Yeah.
over R.
That's Joanne Simpson's.
That's right. So you actually have the data to do
That's
this.
a very good point.
Yeah, also
Thank you.
on this point, kind of comment about your explanation that actually convection is more vigorous because it has less entrainment over land. I think another explanation could be that Well, we know that there is virtually no lightning over ocean compared to over land.
That's right.
Which tells me that there is very little ice in mid-levels in oceanic convection. So your boost, which is, and there is a lot of ice in land systems, which provides this additional boost that can explain that why land convection is actually high, just more freezing, latent heat of freezing.
Yeah, that's a very good point. Yeah, maybe models can help review what role it plays.
But for that you really need ice nuclei information to do it.
Yeah, actually it's funny, you raise a very good point. That's the thing Sue Vandenhever, her graduate student, has been working on for the past 2 years.
This is a very pressing question because there is no real explanation why there is no lightning over ocean and there is so much lightning over land.
Yeah.
And they're kind of comparable in size.
Okay, so the view, Ed Zipser, last time I had dinner with him, he said that his viewpoint is this: the oceanic convection, the ocean environment is too homogeneous. It's really hard to concentrate energy over ocean. Land convection, the surface is so rough, it's easy to bump into a hill and then things get concentrated. So energy is really concentrated. Those core can get really intense.
Over Amazonia is the same thing. Even though Amazonia it's like a green ocean, it's very flat.
Yeah, it's Amazon I think is relatively more
But still it
homogeneous.
has lots of lightning. But there is no lightning over
Then Daniel Rosenfeld will say aerosol plays a role there.
Right.
I don't know.
Yeah, I think the big difference is number one, the dynamic organization, right? Because of the homogeneity. The second is really the cape, the convectivity and stability over land is larger. Because the land surface can warm up much more.
Yeah, but even if you take the similar cape environments, land convection is more vigorous. And I think the explanation is just microphysics. That actually there are more ice nuclei over land, just because it's a dustier place.
If it's the same cape,
right. So
same
people look at that when
size,
they look at similar cape, but still it's lightning like crazy, but it's no lightning over ocean.
So there are no more questions, so let us thank our speaker.
Thank you.
Is there a cause and effect? In other words, to get light from land, you need